Actually, these three stages reaction is already given in exam, but I just want to quickly discuss. I won't take more time. So this is a one proton in the core of the sun, right? Okay, it is moving towards another proton, right? And both have a very high speed, because of a very high temperature in the core and a very large amount of very high density. Okay, so they fuse with each other. Okay, and when they fuse with each other, so what they produce, they make a relatively heavy nucleus that, let's say, moves in this direction, and this is the actually another isotope of hydrogen, which we call deuteron. Okay, as a result, there is another particle, a very small particle is released, and that will move in opposite direction, dear students, to conserve the momentum. And that is a positron. Okay, so it is positron. So this is a positron, as well as a neutrino, which is nearly a massless particle, is also produced. Plus, this is a positron and this is a neutrino. Okay, now dear students, in a stage 2, because all the particles is at the same place, right? So this deuteron, it merge with another proton, right? So when they merge with a proton, now this time they make a helium isotope, He23. So this is a proton and they make a helium nucleus, right? Plus, okay, by the way, this is actually an excited nucleus, right? And then to de-excite, I mean to release the rest of its energy, it release a gamma photon, it's electromagnetic photon, a very high energy carrying photon. Anyways, this is a stage 2. So what is the product of the stage 2? We got a helium, right? So just imagine another helium is produced in another two-stage reaction. Now in a stage 3, what happened, these two heliums, all right, these two heliums, they react with each other, they fuse with each other to make a final stable product of helium. So that is a helium 2 4, plus the two protons are also released. Okay, anyways, our question is about to find out energy in a first stage, right? Just this stage. Okay, and how much energy is released in this stage, the method. Actually, what happened, that energy that is released during this stage is actually coming from some mass that is lost. Okay, so obviously the sum of the mass of the reactants should be greater than the mass of product. Okay, because that mass, which is additional, actually converted into the energy. Okay, so this is a method principle which we always apply. So what should we do? We should first of all find the delta m, which we can find out by adding the mass of the two hydrogens, right, which you can see, and we will subtract it from the mass of this hydrogen isotope plus the mass of positron. Okay, right, so its mass is 2.013550 u. Okay, it's given in a paper, you can check. Plus, this is a positron which have an equivalent mass as of electron. So it should be 0.000549 atomic mass unit. So by taking a difference, we would get that actually what amount of mass converted into the energy, right? So I'm going to calculate it. So finally, we see that its mass is 4.53 times 10 raised to power -4 atomic mass unit, right? This mass is lost. So if you want to convert it into the energy, so you can multiply with 931.5 MeV. And what is the reason for that? Because there's 1 U, which is equals to 1.6606 times 10 to the power -27 kilograms. If you convert this amount of mass into the energy, and you will get answer in joules, and then you convert it into electron volts, so you will get 931.5 equivalent amount of energy, right? And for a reference, you can use this equation, mc squared, right, to get this value. Okay, anyways, so what is our answer for the energy released is, if we multiply, so finally our answer is 0. 0.42 mega electron volts. Now please note that this is a energy release, I'm sorry. So this is energy release in a stage 1, not the entire 3 stages. Okay, so basically there are 4 protons took part. Okay, because you might see there are 6 protons, but you also notice that the 2 protons were released in a last stage. So that's why we can say the 4 protons took part. That's why uh, at a microscopic level I can say that the mass of 4 protons is utilized to get the energy in an entire reaction. Understand? It will be useful in the next questions.